So let me now describe the physical meaning of this transformation that we have made. So again, originally we had the Minkowski metric, dt squared minus dx1 squared minus dx2 squared minus dx3 squared. And we have transformed to a new metric, which, by the way, is called Rindler's metric, d rho squared minus dx2 squared minus dx3 squared. So in all my drawings and discussion, I will ignore these coordinates, which remain untouched during this coordinate change. Now, the first thing I wanted to explain why I say that this metric describes a non-inertial reference frame corresponding to constant eternal acceleration. Let us recall that originally our coordinate lattice was built as follows. It was built as follows. We had original coordinate t, original coordinate x1, and the lines of constant x1 were just vertical lines, and lines of constant t were like this. And what is the physical meaning of these lines of constant x1? These lines are just world lines of observers or particles which are inertial, which perform inertial motion, in this case just stationary. So these are world lines, vertical lines are just world lines of observers, which correspond to dx1 equals to dx2 equals to dx3 equals to 0. Now in new coordinate system, coordinate lattice looks as follows. It's original t and original x1. I just, for convenience, I draw them. And new coordinate lattice looks as follows. So we have lines of constant tau. These are lines of constant tau. And these are lines of constant rho. Rho constant. So who are these hyperbolas? These hyperbolas are nothing but the world lines of those observers or particles which move with constant acceleration, and the value of this acceleration is nothing but just 1 over rho. Different lines correspond to different acceleration, but these are world lines of accelerated observers. That's the reason I refer to this metric as a metric describing what is going on in constantly accelerated motion. So now there is an important issue corresponding to this metric, that it degenerates when rho is getting to 0. What is the physical meaning of this degeneracy? To explain it, consider the following situation. Suppose we discuss, first of all, I have to say that motion with constant eternal acceleration is impossible, physically impossible. Of course, no one can eternally accelerate because it demands infinite energy consumption. So real motions are that someone is moving with acceleration only during a finite period of time. Let us describe that motion first of all. That motion could be described as follows. Suppose someone was static, didn't move until t equals to 0, until this moment of time, then accelerated for a while, turned on acceleration, accelerated for a while, and then continued its motion with the gain velocity. It means that it continued its motion along the line which is tangential to this hyperbola. It is important that any tangential to this hyperbola at any point has the angle which is degree less than 45 degrees with respect to the vertical line. So even if you accelerate eternally, you never exceed the speed of light. Your speed approaches the speed of light asymptotically if you accelerate eternally. But if you switch off acceleration at any finite moment of time, your gain velocity will be less than the speed of light, and the line, your world line will be straight after the switching off of acceleration will be straight line, which has angle less than 45 degrees with respect to the vertical line. So you see, if you accelerate during finite period of time, your world line coincides with this hyperbola only during some finite period, but then it is different from hyperbola. It is important that this motion, if you accelerate for a finite period of time, is inhomogeneous. It is this moment of time when you switch on, turn on acceleration and switch it off is of course different from any other moment on this world line. And the moment, any moment of time on this part of the world line is different from any moment here and different from any moment here. So this motion is inhomogeneous, and that is the reason we do not consider this kind of motions, because in this case we do not expect to get such a nice looking metric. We expect to get such a nice looking stationary metric only if we consider homogeneous eternal acceleration. That is the reason we consider this unphysical situation, which allows us to draw some interesting conclusions. That's the reason we consider this. So now what is important, that if you eternally accelerate, if your forward acceleration is constant, let me remind you that here you decelerate. Starting from the speed of light, you eternally decelerate. Then here you accelerate, actually, because three-dimensional acceleration is always directed along this line. But what is important, that if someone decides at this moment of time, t equals to 0, emit a light ray which tries to catch up with you, this light ray is always parallel to this asymptote and never intersects with the hyperbola. It means that the light ray emitted from any point behind the asymptote never catches up with the eternally accelerated observer. But it does catch up with someone who stopped its acceleration at finite moment of time. Of course, because if you stop accelerating at finite moment of time, you continue your motion along the line tangential to the hyperbola. Because it has angle less than 45 degrees with respect to this line, it is not parallel to this light ray and intersects with it. So only in case if you eternally accelerate, you have this peculiarity that the light ray doesn't catch up with you. How does it reveal, this fact reveal itself in this formula? It reveals itself as follows. Suppose you have a motion with constant velocity along this direction. Then it means that dx1 over dt in our notation is equal to c, which is 1. As a result, ds squared is 0. But if ds squared is 0, here we obtain that d rho over d tau is equals to rho, which is not necessarily equal to 1. It is equal to 1 only if rho equals to 1. So now we obtain a strange situation, that in non-inertial reference frame we obtain that the speed of light does depend on the coordinate. And that has to do with this peculiarity that I just described to you. It becomes even 0 when rho goes to 0, when the hyperbolas degenerate to these straight lines. So if light ray is emitted in the very vicinity of this asymptote and tries to catch up with someone who accelerates, it takes very long time for this light ray to catch up with the acceleration. That reveals itself through this formula. And this degeneracy of the metric is the price we have to pay to consider such an physical situation of eternal acceleration, which has this property that light rays cannot catch up with it. So this is the first thing I wanted to stress. And another interesting observation that one can make here is that, for example, consider an observer which moves, which is stationary in Minkowskian metric. Its world line in these coordinates look like this. Of course, its world line in these coordinates looks as follows. But it is important to stress that for this particle, which is just stationary in original Minkowski spacetime, it takes infinite time tau to get from here to here. In fact, this line corresponds to tau equal to minus infinity, and this line corresponds to tau equals to plus infinity. In new coordinate system, it takes infinite time tau to get from here to here. So if we, for example, try to draw this coordinate system in a rectangular fashion, so it means that we consider, let me stress that we consider rho greater than 0. So we consider lines of constant rho like this. These are just lines of constant rho. and lines of constant tau like this, tau constant, then the world line of this guy, who is just static in the original Minkowski spacetime, in this new way of drawing rho and tau coordinates, will look very strangely. It will just asymptotically approach this line, rho equals to 0, asymptotically approach this line at past infinity, and asymptotically approach this line at future infinity, but will never intersect it during finite period of time tau. So these are all peculiarities of this Rindler metric, which will be necessary for our further discussion in upcoming lectures. It is important to stress just one thing, that this line is called past event horizon of the Rindler observers, of those observers which are at constant eternal acceleration, and this line is referred to as future event horizon of Rindler observers. These are just for notational reasons. Now, what conclusions do we have to draw from all these considerations? I gave you just an example of a coordinate transformation, which is just not linear, because t and x1 have a nonlinear relation to rho and tau, and which transforms us from inertial reference free system to a non-inertial reference system. But we basically drew a different coordinate lattice in the same space-time here. This is the same space-time, but different coordinate lattice. Of course, the geometry of the space, we didn't deform it, we didn't shrink it, we didn't, like, expand it. We just draw different coordinate lattice. Of course, the geometry of the space-time didn't change during this transformation. Also, it is obvious that if one would consider, for example, a motion of a cockroach in this space-time and the same motion of the same cockroach in this coordinate system, this will be the same motion governed by the same physical laws, but observed in a different fashion in new coordinate system. Just in different fashion, but the same physical situation. So it is important that we now are observing a very important thing, which is lies in the core of general theory of relativity, and which is referred to as general covariance. The general covariance is a statement that the physical laws and geometry of space-time shouldn't depend on the coordinate system that we are using, and shouldn't depend on the type of observers that we are using. Different coordinate systems correspond to different observers. That's it.